So just give a few, half a minute or so to allow people to come in.
Sounds good.
Awesome. All right, we'll kick off this party. And so welcome everybody to another day of LRVS EMEA edition. And I'm thrilled and honored to be able to present or introduce, I should say, my friend Jorge Alarcon, who is now the reliability manager for Polaris Laboratories. And today he'll be talking about something that's top of mind and that's happening around the world, right? So Varnish, the causes, the solutions, and he's got some amazing case studies. So we'll go ahead and share this recording he did, and we'll be on the other side for Q&A.
Sounds good. Thank you,
Thanks,
Josh.
Jorge. Yeah.
Hello again, and thank you for your time during this presentation. My name is Jorge Alarcon. I'm a reliability manager at Polaris Lab. And in this 20 minutes, we're going to talk about the situations when the varnish is present in the system. I'll present some interested information that probably it will be useful for all the end users. All right, so let's start saying what is varnish. So from the chemistry perspective, it is a byproduct of an oil degradation. It's mainly an organic deposit. Um, the texture can go from rubbery to very hard texture. And the color is also very interesting because it can vary from a reddish to black, yellow tones. In some cases, I see very funny colors. In some situations, the colors are related with the type of fluid and the conditions on the operational conditions on the equipment. Um, Same thing with the brightness. It can be very bright or it can be very dark. And the most important thing for the end user is that it's very difficult to remove by conventional means. You cannot apply an industrial solvent that you may have on site to remove varnish from the surface of bearings, for example. And we can find the varnish in the oil. We can find it dissolve or suspend. So these are the most common characteristics of varnish. So a study I did on about 500 samples, I found the following information. It's very important to understand this. So around 98% of the samples contain degradation products. It means that these degradation products will enhance the oxidation process of the oil. So as much as greater the concentration of degradation products, the oxidation rate will be increasing too. Um, Around 64% create a layer that grows, and this layer, this surface layer in the surface of the component will reduce the flow, and it will affect the hydrodynamic of the fluid too. So we will have a problem besides these two physics situations, that the heat transfer of the fluid will be reduced greatly too. On the other hand, around 60% of the sample contains solid contaminants. It means this varnish acts like a net, and every time that the solid contaminant is trapped by the net, this hard contaminant will create a wear in the surface of the equipment of the component basically. And around 72% are byproducts that are easily to adhere to surface. And of course, this will reduce the heat transfer again. So every time that we see varnish, the end problem of varnish will be the heat transfer from the hot point to other cool points in the system. So when we see these type of problems, temperature problems, probably is too late, right? Because we advanced to the varnish layer is very large now in thickener, and it will create a lot of problems at that stage. So how's the varnish form? Because we've been talking about varnish a lot of these days. There's a lot of varnish problems, especially in turbo compressor equipment. So how's varnish from the form? So there's a couple of steps that we need to understand how the varnish is created in the system. So the main one, the first step is oxidation. So if we have oxidation, the fluid it will be potentially to create varnish when we talk about certain type of fluids like turbine compressors, hydraulic fluids mainly. So these oxidation, as we described before, will be in the entire process, during the entire process. So it's something that I will continue providing new source for byproducts, and those byproducts at some point will convert in varnish. So the second step is polymerization. So when we talk about polymerization, we're talking about a large change of hydrocarbons that are broken, and when these new molecules are formed, it will try to get together to some others at the same size. So we'll have a small change of hydrocarbon uh, getting together one to another. The third step is solubilization. Solubilization is due to temperature, basically. So we will have a portion of these molecules, new molecules formed here, will be soluble in the oil. So this will depend on the temperature. There's a ratio of solubilization dependent on the temperature, and as higher the temperature, so the product, the byproduct will be more soluble. So when we find varnish in cooler zones, for example, this is the typical situation because in cooler zones, the varnish is still soluble, but the ratio is lower. Then we have the precipitation. So when we talk about precipitation, we are talking about the high molecular weight uh, uh, products in the system. So these will start precipitating into the bottom of the unit, the reservoir mainly. We'll find there a lot of these type of varnish and sludge and stuff like that. So when all these come together, we will have the last point that it's agglomeration. So when agglomeration happens, it's when the problems is really late to work with in some cases. So when we talk about agglomeration, we're talking about large change of of these byproducts that were created here that are not easily to be soluble in the oil anymore because of the high molecular weight. And this is how we came up to varnish, right? So varnish may have different forms, different colors, different states. If we talk about temperature, there are some solutions related to keep the temperature in the system, so the varnish will be dissolved in the entire system, but we will talk about that later. So this is the most important part from the chemistry point of view. So how varnish is formed. So depending on the situation, depending where the varnish in your system is, there are some solutions that can be applied. right? But unfortunately, the problem, when we see the problem, is in this stage when it's too late, right? So we cannot cut the problem here if we were able to identify the problem here or here. So it's every time is the customer send an email and say, I have varnish, I found varnish, there's a sludge in my filter, so the temperature went too high, so stuff like that. So it's this point where the problems are really created and identified. All right, so any other factors that are affecting the varnish formation? So we mentioned that oxidation is the main one. So as far as we have oxidation in the during the process, we will still have in varnish. But there's some others like oil formulation, for example. Group 2 are very prone to form varnish. The quality of the oil in service is very important too. So when we talk about oils that are very degraded, of course we're gonna have those are gonna be prone to form varnish. Depending on the type of oil, we're not talking only about additives, but also about the characteristics of the base oil are gonna be affected. So there's very important to measure how the properties and the additives of the oil are. And of course, temperature. We talk about hot spots in the system. Those are the ones that are going to be harmful for the oil. And this is not related with the system probably, but it's very important. So a lot of people try to understand which is the best way to monitoring the varnish or the health in the of the oil by lab meetings, and a lot of people are looking only for MPC, right? Membrane patch colorimetry. So MPCs is probably it's a lagging indicator. It's not a leading indicator. So we'll need to find a leading indicator like acid number or chemistry changes in the FTIR. Unfortunately, not every lab is capable to measure these changes in a very helpful situation. And of course, the circuit maintenance. We're talking about here the oil circuit, the lubricating system. In many cases, the systems are very contains a lot of dirt, contains a lot of water, so those things are going to affect also to the varnish formation. We can say at some point that those are triggers to varnish from formation. All right, so what else? Some other aggravating factors, of course, not only for varnish formation, but remember that we said the varnish will be acting like a net, and that net will catch, for example, these type of contaminants like water and solid contaminants that will create a problem not to the oil but to the system mainly, right? So keeping the oil that is not in service yet at a good limit. Cleanliness and moisture, for example, is very important before we add in this to the system. All right, so those were the visible factors. What about the non-visible factors? So in a study that I ran in about 1,000 samples, I found that 18% will show in base degradation, right? So the base of the oil was degraded basically, right? For different situations. Around 9% lost the capacity of anti-foam. We're not talking about here on a specific additive. We're talking about the characteristic of the base oil. So the loss of anti-foam additive. 76% are showing problems related with logistics, first in, first out. So we're putting uh, the oldest product at the bottom or at the end of the storage room, and we're not picking up that one. And around 2% are due to quality control issues. Basically, we are not controlling the oils that are into the site. So 98% are not receiving this type of quality control. So what technology is available for varnish mitigation? So it will depend on the stage, of course, as we mentioned before. But we can have deep media filters that are large particles. We can have conventional filters. Of course, these two are very poor to filter the varnish. We can find electrostatic separation, for example. This doesn't remove the source. It will remove the varnish, but not the source of the problem. Anti-agglomerants, for example, and they have a physical limit. It's like an equation when we create when the varnish is being created, the physical limit of the anti-agglomerant will be um, as much as the varnish concentration is created in the system. Another one is a physical chemical filtration, and these will depend on how oxidized is the oil, basically the condition of the oil. And of course, we can use solvents. This will create a dependence on this type of products. Basically, we will have to use it forever until we change the oil. And of course, a physical situation where we can do a modification in the system and keep the temperature of the oil pretty similar during the entire lubricating system. So this will allow the oil to keep dissolving the varnish in all the system. It's a very, very interesting solution, but in many cases, the OEM doesn't approve the changes that need to be made on the turbine, for example. So which one to use? That's the question, right? There's so many options. So which one is the best one? And the best one will depend on the type of problem that the system and the oil is suffering, right? So in a very short case study, we will talk about this a situation that I have with a customer. So it's a gas turbine with an ISO VG32, 8,000 liters, 50,000 hours in service, and the customer decide to do a bleed and feed on about 25% of the oil for no reason, just because they have the oil in the storage room and new oil will come. They decide to do this the bleed and feed process. So at the fourth day after doing this, they notice an increasing on the temperature of about 3 degrees to Celsius. The 18th day, they found varnish mainly in the filters. And basically at the 8th month, they add this anti-varnish filter because of the situation of the varnish that the system is showing. So all these process affect the budget, the maintenance budget, and increasing on around 2% of the operation expenses, right? So what happened after that? So at month 8, the MPC, how do we measure the varnish concentration, was up to 46, 14-month 57 when the filter was in service. So the filter was not able to change the situation, the varnish situation. So they decide to apply for concentration of a chemical fluid that it's designed to dissolve organic matter, to not leave any residue, and to eliminate oil changes. So this is the promise of the manufacturer of this fluid. So again, after a couple of months, the varnish concentration was pretty much the same, even adding that fluid, the chemical fluid. The particles in lab were measured, and the turbine was using a particle sensor at that time. So it was the particle sensor went crazy. It was not able to understand what's happening. And from the filter perspective, they say that they were using one set of filters every 9 months, changing one set of filters every 9 months. But after the problem, after putting the varnish filter and the chemical fluid, they start changing one set of filters every 2 months, right? So an increasing on the on budget again. It's operating expenses going up. So summarizing the case here, no particle count on lab because the site installed a particle sensor in the turbine, which was a mistake. It was very we will be able to catch the problem very easily at the beginning, but they decide to go for this one. No oil quality control on the oil that was used to the for the bleed and feed process, right? So there was no quality control. Um, when the site decide to put the varnish filter in service, they didn't do it based on a root cause analysis. They did it just because they have the supplier knocking at the door for many years until they have this problem. Again, with the chemical fluid, they didn't run a root case analysis. They just use it because they are on the middle of a problem that is getting higher and didn't know what's happening. So as a result of all this situation, the physical chemical they have to do a physical chemical flushing and an oil change. So this flushing and oil change was supposed to do at the year seventh, but because of the unscheduled problems that because of the problems that they are having, they have to do the flushing and changing the oil the fourth year, so 3 years in advance because of this situation, right? So the problem when we were investigating this situation, we found that the problem was the quality control, the missing of the quality control in the bleed and feed oil that was used. So in this case, around 86% of the anti-foam capacity of the oil is not an additive, as the capacity, the property of the base oil was missing due to some situations like poor storage or stuff like that, right? So to conclude, three steps if you are having varnish problems. So the first one is run a root cause analysis. You can use a neutral lab with experience and knowledge in this type of situations. It's very important to work with a neutral lab. So this lab shouldn't be recommended just one specific product. It will be able to recommend a different type of products depending on the situation. Technical evaluation of the alternatives. You can run the lab should be able to run tests and simulations to find out which one is the best option to solve the varnish situation. And lastly, run an economical evaluation of the different alternatives that were selected. Define time and cost of the entire project. So this should be the at least the steps that any site that is having varnish problems should take before making any decision. Unfortunately, the majority of the sites that are having varnish problems, they just jump to a decision with no technical base or technical advice and why to use a product instead of another. All right, so I hope this presentation was helpful, and really happy to share what we have in this conference. So if you have any questions, just I'll be more than happy to answer it. Thank you.
Quite a presentation, Jorge, and you generated loads of questions that came up during the.
I don't know if that's good or that's bad.
What we're here for, right? So to
Yeah, it's good. It's good.
inspire these things and try to answer them as best we can. And it looks as though you've been busy sort of answering those online.
Correct. Yes.
Um, and so for those of you in the audience, if you go to the Q&A section, you'll see that there are open and answered questions. So you can look at the questions that have been asked and then find out Jorge's answers to those. So we'll, use the Q&A and or the chat function to, if you want to ask a few more questions. I think we have about 4 minutes left. Looks like we have another one coming in. Yeah, so questions about MPC, different types of MPCs. Do you want to grab those?
No, so about MPC. So again, the emphasis is a lagging indicator. It's like when somebody had cancer, right? So cancer is not the root cause, right? So if we try to find out what the root cause is, we cannot look at the at a lagging indicator. We should be looking for a leading indicator, and this points to two very simple analysis: asset number and FTIR. And I'm not talking about FTIR looking for oxidation. Turbine oils will probably never going to get oxidation. So unfortunately, there's only a couple of labs in the world that know how to really use the FTIR in this case, combine asset number and ruler in some cases to look for the root cause problem of varnish. So MPC is just a lagging indicator. And I think we have another one. If ruler results lower on MPC, lower or MPC higher, how much oil fresh? All right, so when we talk about bleed and feed, we need to pay more attention not to the physical chemical characteristics of the oil, but also to the performance characteristic. So when I say performance, I'm looking for some others like air release, for example, or RPVOT, stuff like that are more deeper analysis on the properties of the oil. So based on those results, we can do an estimate and say, all right, so you need probably between 10 to 20% of a freshened oil, right? So that needs an explanation deeper on a calculus previous analysis. So it's not like add 20% or add 10%. That depends on the situation. All right.
We got another one coming in. So, yeah, if MPC is higher, whether only replacing fresh oil is the option, or we have to separate a separation or chemical processing necessary, how to flushing procedures to remove form varnish.
Okay, so if the empathy is higher, in this case, again, we need to look for the root cause problem. And the example that I show before in the case study, the problem, the empathy was about high, around between 550 to 60. That's quite a lot for a turbine oil. So in that case, for example, they've been using two different type of products, one filter removal and another type of solvent, chemical fluid, right? But the problem was that the base oil has lost the anti-foam characteristics. So in that case, you can add any type of filter, you can add any type of fluid to clean the system. The problem will remain there, and you will keep having that problem. So again, we need to look for the root cause. Not in my last slide, I mentioned that people only look for the solution based on the economics, right? They completely forget about what is the root cause and to run a simple analysis on the lab. So in this case, if we don't know the root cause of the problem, we cannot say that cleaning is what type of cleaning method is the best one.
So
And go ahead.
if there's no no issues with the base oil, then these are typical responses in terms of you're just dealing with additive depletion and in terms of what MPC is picking up, right? What you're saying is there are base oil issues, right? that are occurring here that no matter, forget about the varnish aspect, you need to fix the base oil issue, right? If it can be fixable, and not every oil can be fixed, right?
That's right.
I think
that's right.
I think
Remember
that's
that turbine oils are 99% base oil basically, and just 1% of type of additive. In some cases, there's no additive there, so the problem is in the base mainly.
Okay. All right. Well, Jorge, thank you so much. This has been
thank you.
awesome. You generate a lot of questions, a lot of interest, and I hope everybody enjoys the rest of the day. Jorge, thanks a lot. Appreciate it. We'll see you.
Thank you, Joe. Have a good one. Bye.